Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young. Chapter 10, Projective Transformations of Two-Dimensional Forms, Section 101, Pairs of Conics. If two polarities, i.e. two conics, proper or improper, are given, their product is a collineation, which leaves invariant any point or line which has the same polar or pole with regard to both conics. Moreover, any point or line which is not left invariant by this collineation must have different polars or poles with regard to the two conics. Hence, the points and lines which have the same polars and poles with regard to two conics in the same plane form one of the 5 invariant figures of a non-identical collineation. Type 1. If the common self-polar figure of the two conics is of type 1, it is a self-polar triangle for both conics. Since any two conics are projectively equivalent, Theorem 9, Chapter 8, the coordinate system may be so chosen that the equation of one of the conics, a squared, is equation 1, x1 squared minus x2 squared plus x3 squared equals 0. With regard to this conic, the triangle 0, 0, 1, 0, 1, 0, 1, 0, 0 is self-polar. The general equation of a conic with respect to which this triangle is self-polar is clearly equation 2, a1 x1 squared minus a2 x2 squared plus a3 x3 squared equals 0. An equation of the form 2 may therefore be taken as the equation of the other conic, b squared, if 1 and 2 have no other common self-polar elements than the fundamental triangle. Consider the set of conics 3, a1 x1 squared minus a2 x2 squared plus a3 x3 squared plus lambda times the quantity x1 squared minus x2 squared plus x3 squared equals 0. The coordinates of any point which satisfy 1 and 2 also satisfy 3. Hence, all conics 3 pass through the points common to a squared and b squared. For the value lambda equal negative a3, 3 gives the pair of lines, equation 4, the quantity a1 minus a3 times x1 squared minus the quantity a2 minus a3 times x2 squared equals 0, which intersect in 0, 0, 1. The points of intersection of these lines with 1 are common to all the conics 3. The lines 4 are distinct unless a1 equals a3 or a2 equals a3. But if a1 equals a3, any point x1 prime 0 x3 prime on the line x2 equals 0 has the polar x1 prime x1 plus x3 prime x3 equals 0, both with regard to 1 and with regard to 2. The self-polar figure is therefore of type 4. In order that this figure be of type 1, the three numbers a1, a2, a3 must all be distinct. If this condition is satisfied, the lines 4 meets the conics 3 in 4 distinct points. The actual construction of the points is now a problem of the second degree. We have thus established figure 100. Theorem 12. If two conics have a common self-polar triangle and no other common self-polar pair of point and line, they intersect in 4 distinct points, proper or improper. Any two conics of the pencil determined by these points have the same self-polar triangle. Dually, two such conics have 4 common tangents, and any two conics of the range determined by these common tangents have the same self-polar triangle. Corollary, any pencil of conics of type 1 can be represented by equation 5, the quantity x1 squared minus x2 squared plus lambda times the quantity x2 squared minus x3 squared equals 0. For the 4 common points being in this case 1, 1, 1, 1, 1, negative 1, 1, negative 1, 1, and negative 1, 1, 1. Footnote: equation 5 is typical for a pencil of conics of type 1, and Theorem 12 is a sort of converse to the developments of Section 47, Chapter 5. The reader will note that if the problem of finding the points of intersection of two conics is set up directly, it is of the fourth degree, but that is here reduced to the problem of the third degree, the determination of a common self-polar triangle, followed by two quadratic constructions. This corresponds to a well-known solution of the general biquadratic equation, chiefly Fine College Algebra, page 486. For a further discussion of the analytic geometry of pencils of conics, chiefly Klepsch, Lindemann, Wöhler-Schugen über Geometrie, 2nd edition, Volume 1, Part 1, 1906, pages 212 forward. Type 2. When the common self-polar figure is of type 2, one of the points lies on its polar, and therefore this polar is a tangent to each of the conics, a squared, b squared. Since two tangents cannot intersect in a point of contact, the two lines of the self-polar figure are not both tangents. Hence, the point B of the self-polar figure, which is on only one of the lines, is the pole of the line B of the figure, which is on only one of the points. Figure 101. And the line A on the 2 points is tangent to both conics at the point A, which is on the 2 lines. Choose a system of coordinates with A equal 1, 0, 0, A equal 0, 0, 1, B equal 0, 1, 0, and B equal 0, 1, 0. The equation of any conic being a1x1 squared plus a2x2 squared plus a3x3 squared plus 2b1x2x3 plus 2b2x1x3 plus 2b3x1x2 equals 0. The condition that A be on the conic is A1 equals 0. That A then be tangent is B3 equals 0. That B then be the polar of B is B1 equals 0. Hence, the general equation of a conic with the given self-polar figure is equation 6. A2x2 squared plus A3x3 squared plus 2b2x1x3 equals 0. Since any two conics are projectively equivalent, A squared may be chosen to be equation 7. x2 squared plus x3 squared plus 2x1x3 equals 0. The equation of b squared then has the form 6 with the condition that the two conics have no other common self-polar elements. Since the figure in which A is polar to A and B to B can only reduce to types 4 or 5, we must determine under what conditions each point of A or each point on B has the same polar with regard to 6 and 7. The polar of x1', x2', x3' with regard to equation 6 is given by a2 x2' x2 plus a3 x3' x3 plus b2 x3' x1 plus b2 x1' x3 equals 0. Hence, the first case can arise only if a2 is equal to b2, and the second only if a3 is equal to b2. Introducing the condition that a2, a3, b2 are all distinct, it is then clear that the set of conics a2 x2 squared plus a3 x3 squared plus 2b2 x1 x3 plus lambda times the quantity x2 squared plus x3 squared plus 2 x1 x3 equals 0. Contains a line pair for lambda equal negative a2, namely the lines, the quantity a3 minus a2 times x3 squared plus 2 times the quantity b2 minus a2 x1 x3 equals 0. Hence, the conics have in common the points of intersection with 7 of the line, the quantity a3 minus a2 x3 plus 2 times the quantity b2 minus a2 times x1 equals 0. This gives Theorem 13. If two conics have a common self-polar figure of type 2, they have 3 points in common and a common tangent at one of them. Dually, they have three common tangents and a common point of contact on one of the tangents. The two conics determine a pencil and also a range of conics of type 2. Corollary: any pencil of conics of type 2 may be represented by the equation x2 squared minus x3 squared plus lambda x3 x1 equals 0. The conics of this pencil all pass through the points 0, 1, 1, 0, 1, negative 1, 1, 0, 0, and are tangent to x3 equals 0. Type 3. When the common self-polar figure is of type 3, the two conics evidently have a common tangent and a common point of contact, and only one of each. Let the common tangent be x3 equals 0, its point of contact be 1, 0, 0, and let a squared be given by equation 8, x2 squared plus 2 x3 x1 equals 0. The general equation of a conic tangent to x3 equals 0 at 1, 0, 0 is equation 9, a2 x2 squared plus a3 x3 squared plus 2 b1 x2 x3 plus 2 b2 x1 x3 equals 0. With regard to which the polar of any point x1 prime, x2 prime, 0 on x3 equals 0 is given by equation 10, a2 x2 prime x2 plus b1 x2 prime x3 plus b2 x1 prime x3 equals 0. This will be identical with the polar of x1 prime x2 prime 0 with regard to a squared for all values of x1 prime x2 prime if b2 equals a2 and b1 equals 0. Since 1, 0, 0 only is to have the same polar with regard to both conics, we impose at least one of the conditions, b2 not equal to a2, b1 not equal to 0. The line 10 will now be identical with the polar of 8 for any point x1 prime, x2 prime, 0, satisfying the condition x2 prime divided by x1 prime equals a2 x2 prime divided by the quantity b1 x2 prime plus b2 x1 prime. This quadratic equation must have only one root if the self-polar figure is to be of type 3. This requires b2 equal a2, and as b2, a2 cannot be both 0. Unless 9 degenerates, the equation of b squared can be taken as equation 11, x2 squared plus 2x3 x1 plus a3 x3 squared plus 2 b1 x2 x3 equals 0. b1 not equal to 0. The conics 8 and 11 now evidently have in common the points of intersection of 8 with the line pair a3 x3 squared plus 2 b1 x2 x3 equals 0, and no other points. Since x3 equals 0 is a tangent, this gives two common points. If the second common point is taken to be 0, 0, 1, the set of conics which have in common the points 0, 0, 1 and 1, 0, 0 equals A, and the tangent A at A and no other points may be written figure 102, equation 12, x2 squared plus 2 x1 x3 plus lambda x2 x3 equals 0. Theorem 14. If two conics have a common self-polar figure of type 3, they have 2 points in common and a common tangent at one of them, and one other common tangent. They determine a pencil and a range of conics of type 3. Corollary: a pencil of conics of type 3 can be represented by the equation x2 squared plus 2 x3 x1 plus lambda x2 x3 equals 0. Type 4. When the common self-polar figure is of type 4, let the line of fixed points be x3 equals 0, and its pole be 0, 0, 1. The coordinates being chosen as they were for type 1. The conic a squared has the equation x1 squared minus x2 squared plus x3 squared equals 0. And any other conic having in common with a squared the self-polar triangle 1, 0, 0, 0, 1, 0, 0, 0, 1 has an equation of the form a1 x1 squared plus a2 x2 squared plus a3 x3 squared equals 0. The condition that every point on x3 equals 0 shall have the same polar with regard to this conic as with regard to a squared is a1 equal negative a2. Hence b may be written x1 squared minus x2 squared plus lambda x3 squared equals 0. Any conic of this form has the same tangents as x squared at the points 1, 1, 0 and 1, negative 1, 0, figure 103. Hence, if lambda is a variable parameter, the last equation represents a pencil of conics of type 4, according to the classification previously made. Theorem 15. If two conics have a common self-polar figure of type 4, they have 2 points in common and the tangents at these points. They determine a pencil, which is also a range of conics of type 4. Corollary: a pencil of conics of type 4 may be represented by the equation x1 squared minus x2 squared plus lambda x3 squared equals 0, and also by the equation x1 squared plus lambda x2 x3 equals 0. Type 5. When the common self-polar figure is of type 5, let the point of fixed lines be 1, 0, 0, and the line of fixed points be x3 equals 0. As in type 3, let a squared be given by equation 8, x2 squared plus 2x1 x3 equals 0. We have seen in the discussion of that type that all points of x3 equals 0 have the same polars with respect to equation 8 and 9. If in 9 we have b2 equal a2 and b1 equal 0. Hence, if a2 and b2 are to have a common self-polar figure of type 5, the equation of b squared must have the form equation 13. a2 times the quantity x2 squared plus 2x1 x3 plus a3 x3 squared equals 0. From the form of equations 8 and 13, it is evident that the conics have in common only the point 1, 0, 0, and the tangent x3 equals 0, and that every point on x3 equals 0 has the same polar with respect to both conics, figure 104. Hence, they determine a pencil of type 5. Theorem 16. If two conics have a common self-polar figure of type 5, they have a lineal element and no other elements in common, and determine a pencil, which is also a range, of conics of type 5 according to the classification already given. Corollary: a pencil of a conic of type 5 can be represented by the equation x2 squared plus 2x1 x3 plus lambda x3 squared equals 0. As an immediate consequence of the corollaries of theorems 12 through 16, we have Theorem 17. Any pencil of conics may be written in the form f plus lambda g equals 0, where f equals 0 and g equals 0 are the equations of two conics, degenerate or not, of the pencil. Exercises. 1. Prove analytically that the polars of a point P with respect to the conics of a pencil all pass through a point Q. The points P and Q are double points of the involution determined by the conics of the pencil on the line PQ. Give a linear construction for Q, chiefly exercise 3, page 136. The correspondence obtained by letting every point P correspond to the associated point Q is a quadratic birational transformation. Determine the equation representing this transformation. The point Q, which is conjugate to P with regard to all the conics of the pencil, is called the conjugate of P with respect to the pencil. The locus of the conjugates of the points of a line with regard to a pencil of conics is a conic, chiefly exercise 31, page 140. 2. One and only one conic passes through 4 given points and has 2 given points as conjugate points. provided the two given points are not conjugate with respect to all conics of the pencil determined by the given set of 4. Show how to construct this conic. 3. One conic in general, or a pencil of conics in a special case, passes through 3 given points and has 2 given pairs of points as conjugate points. Give the construction. 4. One conic in general, or a pencil of conics in a special case, passes through 2 given points and has 3 pairs of given points as conjugate points, or passes through a given point and has 4 pairs of given points as conjugate points, or has 5 given pairs of conjugate points. Give the corresponding constructions for each case. Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.